So tonight we will learn this new section here to study this test for goodness of fit. So if you remember previously, we spent a lot of time to study what we call average. And most of the time we deal with this sample average, right? X bar, if you remember, right? The purpose is we want to understand like what's happening overall, right? Based on this sample average. We try to estimate, for example, we are using the mu for the overall average, right? What's the percentage of people will vote for this candidate, right? So we will get an estimation from the sample. Usually those organizations, they make a phone call survey to like 1,000 some people, right? Get their opinion and then try to make the reference, the conclusion based on those samples response, right? So that's what we have started, right? And then if it's given the population, standard deviation, sigma, then we are using like z-test. Remember, if it's given S, which is the sample standard deviation, we are using t-test. So that's what we learned previously. Most of the time to deal with what? To study average, sample average, right? So there's one thing that here we haven't studied, which is this S, this sample standard deviation, if you remember, everybody. So that's intuitively, how do we understand this S? Remember, S we can consider is the change to the average, right? How the data changed. Is the data like relatively stable? So more or less around this average, the center, or the other way, like sometimes too high, sometimes too low. So this S will tell us like this sample standard deviation. That's the metric we are trying to study, right? So if we study more and more for this sample standard deviation, we realize this S turns out follow a new distribution. Everybody, we call this chi-square distribution. Chi-square distribution. So you can see the alphabet letter X, right? So I mean, we don't call that X square distribution. So in statistics, we call this chi-square distribution. Okay. Now, what's that chi-square distribution look like, right? So to give you a intuitive understanding based on the picture, right? I mean, usually we say one picture was thousands of words, right? So remember, normal distribution, right? What's that look like? Normal distribution, we know that's the bell-shaped, right? You can get a positive, you can get negative, right? So you have both sides. Remember, that's what we usually call like Z, like standard normal distribution, right? The Z table, Z curve, right? And then the second one we have started is we call this T distribution, right? It's also a bell-shaped curve. You can get a positive, you can get a negative, right? And then here we introduce this concept, DF, degree of freedom. So in other words, if you have different degree of freedom, then you have different kind of curves, right? The lower, the higher than degree of freedom, that means the more standard the curve will be. So you can understand that way, right? So that's the T distribution. That's the one we have learned, right? Tonight, we are going to learn this chi-square distribution. Now, if you compare those three graphs, you will see some difference, right? So number one, you only got a positive, everybody. You see, there's no negative here, right? There's nothing about negative, okay? Number two, is bell-shaped. Yes, it is bell-shaped, okay? But it's not symmetric like the previous one. The Z curve or the T curve, right? They are symmetric. But now chi-square distribution is not symmetric. It's like a tail to the, what's it said, right, tail to the right, right? It's like skewed, right, everybody? Right, so here we also have this concept of degree of freedom, similarly, okay? So that's in terms of picture, what's the chi-square distribution look like, okay? Now, we will have example to help us like study exactly how do we apply the chi-square distribution to do the hypothesis testing, okay? So this is a practical example we are studying. So we did a random sample of 100 consumers for their favorite like flavor preference. So we are asking people their favorite flavor. So we have a choice here: cherry, strawberry, orange, lime, grape. 1, 2, 3, 4, 5 different flavors, right? So we are trying to see, do consumer people, do they have preference for certain flavor, right? If you think about that in reality, right, it's going to be very useful for those like soft drink companies, right? When they are trying to produce like those kind of a soda, right? Do they produce equal amount, or they have to produce more for certain flavor, right? So that's the case that we have to, we want to understand, which is intuitively very useful, right? So we ask altogether 100 people, everybody, right? Out of these 100 people, we got the answer, 32 of them, they like the cherry, 28 strawberry, 16 orange, 14 lime, grape, 10. So that's what we call observed, everybody. We are using capital letter O for observed. So in other words, I can write down like O1 is equal to 32. O2 is equal to 28. O3, 16, so on, right? And then if we assume all the consumer has an equal preference, right? Remember H0, if we do the hypothesis testing, right? Actually, I can write down this, I can mention this here. When we write down H0, we mentioned that previously always equal, right? So this case here, we are trying to study consumer, do they have an equal preference or not, right? So in that case, we say consumers show no preference for the flavor. So in other words, if we are using a proportion, right, we have 5 different proportions. They should be all equal to each other. That's our H0, right? So if that's the H0, if we expect all the consumers has equal preference, right? So we break 100 into how many groups? 1, 2, 3, 4, 5. 5 equal groups, everybody, because the H0 tells us they should be equal, right? So 100 divided by 5 equal groups. How many people in each group? 20. That's the reason we have 20 here, everybody. We call this expected. How do we derive this? It's coming from our reference here, right? So H0, we say there's no preference for the flavor. So that's what we expected. Capital letter E for that. So we can write down capital letter E1, 20, E2, 20, and so on. Is that clear? So I can write down the, like that, right? So you can say this is our O, this is O1, this is like O2, right? Can you say that, right? This is our E2, right? And so on, like O3 or E3, like that. Okay, so what's H0 here? So H0 here, they are asking, based on the sample of 100 people, right? Can we say there's a significant difference, right? The significant different preference for the flavor at alpha equal to 5%. So in other words, we are trying to see, do they equal, or as long as one of them showed a significant different from the other, then that is H1. In terms of which one, we don't need to know, right? As long as we know one of them is significantly different from other, that's good enough. Okay, so that's our H1 here. So we are trying to do the 5 steps hypothesis testing, right? Try to understand how we can use the hypothesis testing to solve these practical questions. So far, so good, right? Now, second part, we are trying to calculate the chi-square distribution, everybody, chi-square distribution. So we have the formula here. We always want to cover the calculation first. So let's stick with the same procedure, right? Do the calculation first. So we are going to use this formula here, everybody, this formula. Chi-square is equal to the summation of OI minus EI bracket square divided by EI. What's OI? That's what we say observed outcome, right? What's the EI? That's the expected outcome. So if you remember, we just covered that here, right? Remember, this is O2, this is E2, right? This is O1, this is E1, right? Now we can plug into this equation here, everybody. This formula here is a relatively simple formula. It's not that straightforward. So pay attention to the rest of 1 or 2 minutes if you care about the final. Okay, so what's happening, how we are going to calculate this chi-square statistics, right? Using this chi-square formula, everybody, this formula here, right? So what does that mean here? We are going to use, when I is equal to 1, so we are going to plug here, O1 minus E1 bracket square. Everybody, follow me? O1 minus E1. Let's check out. What's O1 here? O1 is 32 minus E1 is 20. So 32 minus 20, let's see if that's our first term. You see that here, right? So this first term, we are trying to get that, right? So it's 32 minus 20, O1 minus E1 bracket square divided by E1, right? That's the first term, E1. Similarly, for the second term, this is the second one here, right? So what's O2 minus E2 when I is equal to 2, right? Bracket square. So what's O2? We can check O2, that's observed, right? Observed 28 minus 20. Check. Is that 28 minus 20? Yes, divided by 20, which is the E2, right? Square. Similarly, for the O3 minus E3 bracket square divided by E3. Everybody, if you have some time tomorrow, try to review this example here so you understand how do we calculate this chi-square statistics. It's going to be very important, everybody. And I'm pretty sure on the final, we will have some questions asking you to do those calculations here. The calculation itself is not that complex, okay? It's not that complex. It's a bunch of numbers, but make sure you know how to do that, right? Now, we add all of those 1, 2, 3, 4, 5 terms together, right? So we have, there's a typo here. This one should be what? I equal to 1 to 5, right? We have 5 groups, should be 5, right? So if you have printed out your next notes, you can change that one here to be 5. Okay, that's 5, not 6, because you check 1, 2, 3, 4, 5. All right, now, after we do the calculation, we find out is the value from the data from the test, 17.0, right? Now, after the calculation, we always go back to the this step here, right? So previously, after we are using the formula, right? Then we are trying to decide, are we going to use the p-value method or critical value method, right? Previously, we mentioned that whenever we see T formula, then we have to use critical value method. No other ways, right? But if you are using Z formula, you have 2 choices, either the critical value method or the p-value method, right? Now, for this chi-square, everybody, this chi-square formula, which method we should use, everybody? We should use critical value method. No other choice. If we use the p-value approach, we have got a trouble. Okay, so we have to use the critical value method to solve this problem here. Remember, how do we find out critical value, right? So where do we get this critical value? Critical value is coming from where? From a table, right? Table. So which table we have to use depending on which formula we are using here. We are using the chi-square formula. That means we are using this chi-square table. Everybody? So that's the last table we are learning for this class here. Okay. And that's the last table that we required. Okay. So you will either print out or, since we don't have the in-class exam, otherwise you have to print out and bring that to the class, right? So you will need to use this table here, the chi-square table, for some homework questions and for the final questions. This is the chi-square table. We mentioned that earlier, right? It's a bell-shaped curve. It's not symmetric, right? You only take the positive value here. You only take the positive value. Okay, so this one-page chi-square table, how do we use that? Okay, everybody? So let's see. There's a very important thing here. This table, when we check this one, the shaded area is equal to alpha. The probability to the right of some number here is the corresponding that alpha. Okay, that is a corresponding that alpha. Okay, so how do we understand that, right? Let's use some example here. This lecture notes example here. So we have our alpha is equal to 5%, right? So 5%, let's see, alpha is 5%, so that is, let me see. Let me erase this one here, you don't get confused, right? Alpha is equal to 5%, everybody. Where is that? That's this one here, right? Is that 5%? Everybody follow me? 5% here, right? Now, degree of freedom. Degree of freedom for the chi-square distribution, we are using the same formula, which is n-1, degree of freedom, right? So what's the n is the sample size, right? But what's the sample size here we have? Everybody, we have how many people here? We are asking 5 groups, right? 5 groups, 100 people. Everybody, don't get it confused, okay? So the one that we are using here is for each group, right? For each group here, let's go back. For each of those 5 groups, right? Do they equal or some group is significantly different from that, right? So that's the degree of freedom, 5 groups minus 1, which is 4, all right? So go back to our table. Let's see. Chi-square, right? Now we know this 0.05 is this one here. Degree of freedom, 5 minus 1, which is 4. Everybody, this table here. 5 minus 1, which is 4. So 0.05, remember, the critical value we are getting is what? 9.488, everybody? So those are the critical value. I have that here on the lecture notes, 9.488 coming from. And you see those, all those numbers here, everybody? Those critical value, which means some value on this x-axis here, can only be positive. We don't have anything about the negative, okay? So follow me, that's the way to find out what's the critical value. Depending on number 1, what's the alpha? Alpha is 5%. If it's not given, should it be 5% by default, right? Second one, which row to choose from, depending on DF, degree of freedom, which is n minus 1. What's n? Number of groups. So 5 minus 1, 4. So give us 9.488. That's the reason we got this critical value, everybody. 9.488, that's our critical value. I can draw a critical line here like that, right? So some people may have some questions, right? Do we have to worry about, is that a one tail or two tail? Is that right, everybody? Is that one tail or two tail? So if you pay attention to these hypothesis testing here, right? So actually, it's a very special one if you think about that, right? So H0 is always equal. It's what? It's a multiple group, right? H1 is what? As long as you find out one group different from the other, right? It's higher or lower, doesn't matter. So in a way, you can understand this is kind of a two-tail if you really want to classify that, right? But because of the table here, they didn't specify one tail or two tails. So in other words, we simply want to use alpha, everybody. Whenever we are given the alpha, we just use that alpha here directly. Okay, so you don't have to worry about one tail or two tail. So you don't have any confusion for that. Hopefully it's clear. Now, we got this critical value here, 4.488. Where's our data, everybody? Data tells us 18.0, right? 18.0, like data from the calculation is what? It's like further away, everybody. It's like 18.0, which is further away from what we call the center, right? Center is what? HO. Center is HO. So the data is further away. For example, here is 18 point something, right? It's further away from the center. So what are we going to say? Reject. Reject what? HO. So conclusion here, right? Make a decision at step number 4. Reject HO. Step number 5, right? Summarize using the human being language, right? To summarize, when we say reject HO, what does that mean? So going back to here, reject HO, that means HO is not right, right? That means H1 is right. Why do we care about H1? H1 is the claim. The claim is trying to see, based on the sample of 100 consumers, right? Can we say there's a significant difference, right? For those consumers' flavor preference? The answer is yes, H1 is right. We have 95% of confidence to say that. Okay. So I write down here as only one tail, everybody. I don't want you to get confused for that here. So the best way to think of the chi-square test, you think about that the alpha is always the one. If it's given alpha, we are using that directly for the table. We don't need to divide by 2 or not. We don't need to worry about that. So in the table here is always that alpha. So that's in terms of this example. Now we know the consumers, they do have a preference. I think that's intuitively reasonable, right? I mean, usually when we go to those vending machine, for example, some vending machine at school, right? You will see sometimes like some soda always running out first, right? I remember I went to the vending machine a few times. I think it's like one of my favorite soda is Mountain Dew. I mean, some vending machine, they even don't have that, I think, right? You have to request. Like sometimes you see those people try to load more soda. You can talk to them. Hey, can you put some Mountain Dew, right? That's my favorite. A lot of sugar, right? I'm not healthy. But I think that one is easily running out, right? You will see that, or some other flavor may running out. So in other words, when those soda company like a Coca-Cola, when they produce, right, those different flavor, they are not going to produce the same amount for different flavor, right? So they are going to produce certain flavor. They are actually find out people like that more, so they will produce more. So that's in terms of this example here. Some notes I want to put that here. Number one, the data must obtain from a random sample, right? So we, at the beginning, we say we're asking 100 random consumers, right? So random consumers, that means you want to cover the population, the potential population for that, for your market research, right? If you are trying to design a soda for example, young people, right? You may want to focus like either college students or like high school, right? Or like relatively young people, right? And try to, get it at random. So you don't want to choose like all the samples are coming from boy or coming from girl, right? So try to get a, good representation of your consumer well-being, right? Now, second one, to use the chi-square formula, we usually require each expected outcome. Everybody, EI here. So what is EI? Let's go back to here. So we have this observed, right? So that's the one we find out from the data. What we find out from expectation, expected, E, E1, E2, right? Remember, how do we get this one equal to 20? Because we have, altogether, we have 100 people. If we assume all of them, they have an equal preference. So they are dividing by 5 equal group, each group 20. That's the 20 coming from. So usually when we are using a chi-square formula, we require this number here to be greater or equal than 5. So right now, what we have here is 20, which is good. So it's reasonable to use the chi-square formula. If it's less than 5, then in statistics, we have some other more complex way to do the calculation, not using this chi-square formula. Now, question here, why do we call this is a goodness of fit test, right? So how do we understand that? So if you study like the output, for example, like this way, this table here, right? We have 5 groups, right? And we find out sometimes they're high, sometimes they're low, but most of the time it's like a little bit above, a little bit below, right? So in that case, is from a picture, you can say it's like more or less they are equal, right? That's a good fit, right? And now, if the other case, out of those like 5 groups, you find out that certain groups is extremely high, the other group is extremely low, right? So you can see that this fit is not good because it's like go to the extreme side, right? It's not that equal side. So in that case, it's not a goodness of fit. Is that clear? So that's the concept of when we say goodness of fit, right? So using the chi-square formula to do the calculation. Everybody?